Why was Newton's classical physics failing in the 20th century? What are the phenomena it couldn't explain? Why was Max Planck dissatisfied with his own discovery? How Einstein came up with his Nobel Prize winning theory? How was Niels Bohr inspired by Einstein? How did all this advance the understanding of structure of atom? Find out all this along with a fun fact at the end. Till now, we have discussed how in the 18th and 19th century, scientific advancements on the back of experiments in various fields of physics led to a model of atom. J.J. Thomson discovered that subatomic particles exist, starting with electron. Rutherford modified the model to have a small positive core with electrons circling it. However, as discussed before, Rutherford's model couldn't stay for long because it violated the classical principles of electromagnetism. In the first half of 20th century, classical physics was not able to explain many important phenomena at its limit. The mere four being blackbody radiation, photoelectric effect, temperature dependence of heat capacity of solids, and atomic line spectra. Let's try to see why and how these phenomena were beyond the scope of classical physics. First, let's delve into classical mechanics explanation of blackbody radiation and what was wrong with it. Kirchhoff, who discovered laws of spectroscopy, also came up with Kirchhoff's law of thermal radiation. Kirchhoff postulated that for a black body which absorbs all wavelengths, spectral radiance, which is radiation energy per area per frequency, depended on temperature. Throughout 19th century, physicists tried to come up with a formula for spectral radiance. Rayleigh modeled light as a wave and derived a formula where the radiance was proportional to T and inversely proportional to wavelength power 4. However, at low wavelength of electroviolet rays, this formula predicted infinity and diverged from empirical values. This was called ultraviolet catastrophe. In 1896, Wilhelm Wien came up with a formula which worked at low wavelengths of ultraviolet rays but failed at high wavelengths. So in 1900, Max Planck tried to mathematically converge these two formulas. His results matched the empirical values and solved for the ultraviolet catastrophe. However, what came out of mathematics changed the course of physics forever. It required that light energy cannot be calculated like waves having continuous intensity, but as whole number multiples of a base energy. This base energy is Planck's constant multiplied by frequency. However, Planck was himself not convinced that energy was not continuous. This changed after Einstein applied Planck's concept of quantized energy to photoelectric effect. Next, similar to blackbody radiation, the theory and empirical evidence on specific heat of solids were not matching. In 1819, Dulong and Petit had shown empirically that molar specific heat of solids at constant volume for all materials is constant. This was valid for high temperature for simple solids. However, it failed to match the data at low temperature. Dulong and Petit matched the classical statistical theory where one can consider solid as atoms with three vibrational modes of freedom and by equipartition energy distributing the energy equally in the three modes. However, when there is lower amount of energy to distribute, Einstein and Debye used another statistical model similar to Max Planck where the atoms and molecules can have finite number of states and finite amount of energy. This model matched the empirical evidence that at low temperature specific heat was temperature dependent, but at high temperature it matched Dulong and Petit law. Later, the photoelectric effect was discovered in 1887 by the German physicist Heinrich Hertz. Hertz observed that shining ultraviolet light on two metal electrodes changed the voltage between them. In 1902, Philip Leonard demonstrated that when electrically charged particles are liberated from a metal surface when it is eliminated, and that these particles are identical to electrons. However, the issue was that the maximum kinetic energy of the released electrons did not vary with the intensity of light as expected according to the wave theory of light. but was proportional instead to the frequency of light. Another puzzling observation was that there was virtually no time lag between the arrival of radiation and the emission of electrons, while in wave theory, it would take time for energy to build up to a threshold value. In 1905, Einstein used Max Planck's energy quantization concept on photoelectric effect. If energy was quantized, it meant that a minimum frequency was needed to give electrons enough energy to leave the metal surface. However, this raised another question. Was light a wave or particle? It behaved like an electromagnetic wave while traveling, but like a particle when being absorbed or emitted. Taking inspiration from Max Planck and Einstein, in 1913, Niels Bohr postulated that electrons revolve in discrete orbits around the nucleus which had fixed energy levels. If electron moved from higher energy to lower energy orbit, it emitted photons with the differential energy. This model explained emission spectral lines of hydrogen atom. In 1932, James Chadwick passed alpha particles through beryllium. He noticed new particles which had mass same as protons but had no charge. He called these particles neutrons. To summarize this video, we saw how classical physics phenomena were not able to explain blackbody radiation, specific heat capacity of solids at low temperature, and photoelectric effect. Max Planck, Einstein, and Debye used energy quantization concepts to solve for them. In 1913, Niels Bohr gave the concept of fixed energy states for electrons. However, this model didn't explain emission spectra for atoms with multiple electrons. In 1932, neutrons were discovered. So, by 1932, we had the model of atom where there is a positively charged nucleus consisting of protons and neutrons and negatively charged electrons revolving in discrete energy orbits around it. But is electron moving in circular two-dimensional orbit around the nucleus? Isn't the world around us 3D? What happens when an atom has multiple electrons and multiple electrons jump from one state to another? How are emission spectra formed then? Bohr's model was also not complete. Further, there were new emerging questions. Why was energy discrete? What was light, a wave or particle? Why was classical mechanics failing to explain multiple phenomena? We will address these questions in the upcoming videos. Now for a fun fact. Did you know that there is a movie made using actual atoms? Yes. The movie is called A Boy and His Atom. IBM researchers used carbon monoxide molecules under a scanning tunnel microscope which magnifies them 100 million times. They moved the two atom molecule and took images. These images were put together to form a 1-minute short movie. The movie was recognized by the Guinness Book of World Records as the world's smallest stop-motion film in 2013. The research was being done to understand data storage at atomic level. But the researchers wanted to create this movie to imbibe curiosity in students about science. In 2012, IBM demonstrated that a bit of computer memory could be stored on just 12 atoms instead of a million atoms, which is the current minimum. If this is successful, it would mean we could carry not just 2 movies, but all the movies ever produced on our phone. So, who is your favorite physicist from the early 20th century and why? Please comment below. Do let us know the topics on which you would like us to make more videos. Don't forget to like, share and subscribe to our channel. Just